Hello, my name is Sebastian Vuskovic. I'm a fourth-year mechanical engineering major at San Francisco State University. For the course Engineering 470 Biomechanics with Dr. Azadi, we were asked to write out a paper on biotensegrity and its relation to cellular mechanics and the cytoskeleton. I chose to take Dr. Azadi's course on biomechanics as I really enjoyed my mechanics of solids course I took a year ago, and I really wanted to apply these concepts to the human body. This report will explain the background of tensegrity, which was first coined in 1949, and from tensegrity came biotensegrity, which was the study of rethinking and understanding human movement. All right, I'm going to share my screen right now. Cool. Put me over here. Okay, let's get this project started. All right, so as I said, this will be my tensegrity project on biotensegrity on the structure of the cell. And this right here is a little design of a simple tensegrity model. We'll get to that right away. So a little outline of my presentation. I'm going to start with my introduction to tensegrity. What is biotensegrity? I'm going to review on cell functions and the cytoskeleton, how biotensegrity can help our understanding of cell mechanics, a conclusion, and a quick thank you. So the word tensegrity comes from the two words tension plus integrity. And tensegrity was first thought up by Buckminster-Fuller, which is down here. I'm circling right now. Buckminster studied engineering, architecture, and was a poet. And his idea for tensegrity was to be a new type of architecture that resembled nature instead of being built by humans. Even though tensegrity was thought of by a human, we'll give him the benefit of the doubt. Tensegrity is a design principle that applies when a discontinuous set of compression elements is opposed and balanced by a continuous tensile force. And this all creates internal pressure that stabilizes the whole system. So in this gift we have on the top right hand of the screen, we can see this is a simple tensegrity model, and the green bars are in compression and the red bars are in tension. So a quick little refresher, basically compression stress is when an inward object presses inward and it causes it to be compacted, and tension is a state of stress with the materials being pulled apart. So Buckminster-Fuller, who did art and engineering, same thing can be done with tensegrity, which can be applied to engineering, art, and even biology. So what is biotensegrity? So combining the studies of biology and tensegrity, we get biotensegrity. Biotensegrity can be viewed as a study of biology, but with the features of tensegrity in mind. And we know that the study of biology is a study of living organisms. And one of the core concepts of biology is evolution. We know that evolution is the change of characteristics of a species over several generations, and this process relies on natural selection. So we could apply the idea of evolution, and we could say that evolution brought upon tensegrity. And the idea that tensegrity could have been with us since multicellular organisms, which was 3.7 billion years ago, and because of evolution has gained traction. We have this video I'll play in a second. It was made by Tom Flemons, who designs tensegrity models based on human bone structure. So Tom Flemons, in this design right here, the TENS is all built by tensegrity joints. And Tom Flemons, I'm going to do a quick little quote while this is playing by Tom Flemons. He says that evolution selects the structural applications which are maximum efficient. And this is tensegrity structures, which combine flexibility, resilience, and strength with minimal energy and material requirements. So this is basically showing how tensegrity can be applied to bone structures. I will say this video is a little uneasy to watch. It's a little scary, but it's pretty cool that this was built. Tom Flemons is a really cool guy. I recommend looking him up. Okay, so we're going to do a quick little review on the cell functions and the cytoskeleton. So over time, living things on Earth have evolved into thousands of different species, though we all share one bond. We all have cells. So there are three main parts of a cell. As we can see in this image over here, we got a cytoplasm, which is the fluid inside of the cell, a nucleus, which is where all the essential information is stored, DNA and RNA, and we even got the cell membrane, which is protects in the cell and keeps everything inside. Okay, so the cytoskeleton can be a part of the cell that I believe can be overlooked. Its function in the cell is to maintain the cell shape and change how the basically it can also change the cell's shape if need be based on its function. And the cytoskeleton is a network of protein fibers that are all interlinked, as we can see in this picture over here, and they extend from the nucleus. That it also provides mechanical support to the cell. So how can we apply this to biotensegrinity, and how can we help our understanding of cell mechanics in the cytoskeleton as well? So core principle of tensegrinity is that it offers high flexibility and strength with low work input. And by applying biotensegrinity to cell mechanics, we could potentially know how our bodies make our cells and even how those cells interact with other cells in our body, which would be amazing. Dr. Engr, who is a leading scientist in the biotensegrinity field, he used the tensegrinity model to rethink how we view the cytoskeleton. So in this first image up here, we have a basic idea of the cytoskeleton. It's all these fibers coming out of the nuclei. It's all kind of like mushy. But Dr. Engr made this cool little model here, which is basically the cytoskeleton concept with tensegrinity principles in mind. So I believe that the key to the puzzle is the cytoskeleton. If we can understand how cells change shape to satisfy a function, that's just crucial. Meaning it's just starting from the bottom, and we could keep on going up and just proving that our whole body functions use tensegrinity. And applying the tensegrinity model to the cytoskeleton model, as Dr. Engr did, could be the start of a new era in biology, with biotensegrinity taking center stage. A quick little quote by Dr. Engr, he basically said that understanding the design principles behind how we build patterns like cells is very important. Like a good example is Jurassic Park. You know, the scientists, they made dinosaurs, but like nothing could beat how nature builds it. And understanding how living cells and tissues are constructed so that they exhibit their incredible organic properties, including abilities to change shape, move, and grow, is just incredible. And it'll be amazing if biotensegrinity can lead the way to understanding that. So quick little conclusion, tensegrinity can be applied to more than just engineering. As discussed, it can even possibility explain how cells cytoskeleton operates. Tensegrinity is at heart an art form that resembles nature, and that can be applied to engineering. A cool little model of tensegrinity that really helped me understand the principles of tensegrinity was on the right, was built by Legos. And the Lego chains are in tension and the beams are in compression. And I'm going to be building that one day. You can mark my words once I get these Lego pieces. So biotensegrinity has the potential to become extremely relevant in the future by giving us better understanding of cellular mechanics. And just understanding the cellular mechanics with biotensegrinity is the first step in proving that tensegrinity is used throughout all living organisms. And I hope there's a breakthrough with our understanding of cell mechanics. And cell mechanics and the cytoskeleton, and biotensegrinity will have to lead the way for these discoveries. All right, thank you. I hope you enjoyed this presentation. This is my email and LinkedIn. If you have any questions, my presentation, don't fret on email me. Don't worry, I'll be happy to answer any questions. And I hope you have a good day. Thank you.